Welcome to Probability and Statistics, section 3.2. We're talking about conditional probability today. So topics to take note on are conditional probability, the definition, the notation, and the formula. And then we're going to look at inverting probabilities. And we're going to also look at probability trees. And that's going to be the three main things that we talk about for this section. Okay, let's look at an example. Researchers randomly assigned 72 chronic users of cocaine into three groups using different drugs. Desipramine, which is an antidepressant, lithium, which is the standard treatment for cocaine, and a placebo. Results of the study are summarized below. So relapse and no relapse. Okay. So what is the probability that a patient relapsed? So the probability of the patient relapsed is the number of people who relapsed divided by the total. 48 divided by 72. So that's roughly 67%. Okay. So what is the probability that a patient received the antidepressant and relapsed? Okay. So now, if you're doing and, so as you'll see in this section, the words and or and given are really important, and you want to like look for those words. So in this case, and. So what is the probability that they got both of them, got that drug and relapsed? And that's the people who got the drug and relapsed, 10 people, divided by the total, 72. So that's about 14%. Okay, so now we're going to talk about the conditional probability. The conditional probability of an outcome is, now remember this notation from last section, the straight line you read as the word given. So P of A line B is read probability of A given B. And it's equal to the probability of A and B divided by the probability of B. Okay, so let's say we want to look at the probability of relapsed given that they took the desipramine, is to do the probability of the and divided by the probability of taking that drug. So probability of the and is 10 out of the 72. Probability that you had the drug, the total of the drug is 24 out of 72. And so then that goes there. And you'll see that they have both the same denominator. So it simplifies to be 10 over 24, which is 0.42. So another way to do that, to kind of like you're going to always get the same denominator, is just say the probability of the given means you go to the whatever row or column is the given. And then you do probability using that total, 10 out of 24. Okay. So if we know that a patient received the antidepressant, what is the probability they relapsed? So we focus on the row. 10 out of 24 is 0.42 or 42%. Okay. Probability of relapse with lithium is 75%. And the probability of relapse with placebo is 83%. Okay. So let's see. Now, if we know that a patient relapsed, what is the probability that they received the antidepressant? So if they relapsed, the probability they took the antidepressant is 21%. Probability they took lithium, if they relapsed, is 18 out of 48, because we're dividing by the total for that given. So the given is relapse, we're dividing by that total. So 0.38, and probability of placebo given that they relapse is 0.42. Okay, so earlier we saw that if two events are independent, their joint probability is simply the product of their probabilities. If the events are not believed to be independent, the joint probability is calculated differently. So remember last time we had how to do OR, how to do probabilities with OR, and and that was different for if they were disjoint or if they were not. And then we had a general formula. And then last time we looked at like doing and multiplying probabilities, and we only did a formula for if they're independent. We never told you a formula if they're not independent. And so we can now tell you the full formula, the general formula for all cases. The probability of A and B happening is the probability of A given that B happened times the probability that B happened. Okay, it's not multiplying probability of A times probability of B. Now notice that if they're independent, then this is just probability of A, because if A and B are independent, then knowing B tells you nothing about A, so probability of A given B would be the same as probability of A. So the formula from last section was a simplification of this formula. This is the true general formula. All right, it's useful to think of A as the outcome and B as the condition. All right, let's do another example. Consider the following hypothetical distribution of gender and major of students at an introductory statistics class. So let's say we've got 50 female and 50 male students, and 60 of them are in the social sciences and 40 of them are something else. So the probability that a randomly selected student is a social science major is, think about it, think about how you'd answer. All right, 3, 2, 1. The answer is 60 out of 100, so 0.6, 60%. These are really nice numbers for doing percentages. All right, the probability that a randomly selected student is a social science major given they are female is, now, like, think about it yourself. How would you solve this? 3, 2, 1. Oh, my camera's, my picture's in the way. All right, 30 out of 50, which is also 60%. Okay, so since social science given like male or gender also equals 0.6, major of students in this class does not depend on their gender. So we get this formula right here. And that's the formula for two events being independent. Okay, generically, if probability of A given B equals probability of A, then the events A and B are said to be independent. Conceptually, is independent means like knowing B doesn't tell us any information about A. So mathematically, we know that A and B are independent if probability of A and B equals probability of A times probability of B. So probability of A given B equals probability of A and B over B equals probability, and then assuming this connection right there is assuming that they're independent. And then, so then we get that independent events means that these things are equal. All right. Now, we're going to look at a situation involving breast cancer screening. So American Cancer Society estimates that about 1.7% of women have breast cancer. And so the Susan G. Komen for the Cure Foundation states that mammography correctly identifies about 78% of women who truly have breast cancer. So an article published in 2003 suggests that up to 10% of all mammograms result in false positives for patients who do not have cancer. So when a patient goes through breast cancer screening, there are two competing claims. The patient had cancer and the patient doesn't have cancer. If a mammogram yields a positive result, what is the possibility that the patient actually has cancer? And we can do this with a decision tree because there's an unknown there. Like whether or not they actually have cancer is unknown. And then we can kind of look at the unknown and then split it up. So then we're relying on the 78% chance of seeing a positive up there. So that is from the Susan G. Komen number from the last slide, and this is from the third element from the last slide. And so then if we've got roughly 1% of, like 1.7% of women who have cancer, and then so then we can multiply these numbers. So when you go through, multiply, and you get 0.0133 and so on and so forth for the other three options. Okay, so let me erase my, so the probability of cancer, given that they are had a positive result, is the probability of cancer and positive divided by probability of positive. And so that's probability of positive is this one and that one, because they could be, it could be a true positive on the top or a false positive on the bottom. Okay, so that's 0.12%. So that means if a woman goes through and through one of these mammograms and tests positive, there's still only a 12% chance that she has it because of the imperfection of the test, and because of there's so many more people who don't have cancer compared to people who have cancer. It really skews the result. Okay, so tree diagrams are useful for inverting probabilities. Okay, so what we want to know is the probability of cancer given positive, and we know the probability of positive given cancer, right? And so the tree diagram helps us to invert that conditional. All right, let's try a practice question. Suppose a woman who gets tested once and obtains a positive result wants to get tested again. In the second test, what would we assume to be the probability of this specific woman having cancer? Okay, I want you to think about this. You should probably even stop your video and try to compute this. All right, I'm going to pause my recording and do it myself. Okay, the correct answer is 12%. That's from the last slide, really. Okay, but now we're going to ask a harder question. What is the probability that this woman has cancer? Second mammogram also yielded a positive result. Okay, so pause your video and do a tree diagram like 2 slides ago and see if you can figure it out. Okay, I'm going to give you the answer now in 3, 2, 1. So the correct answer is 52%. And the reasoning is that you do the same tree diagram as last time, but you change the probability that that woman has cancer. So before, that number was based on the total number, total proportion of women who have cancer. But now she's already had one test, and we figured out that the probability she has cancer is now 12%. So then we change that to be 12, and then we do it again. And you take these numbers here and you add them together. Now I'm all over the place because I'm in the way. All right. And then so then you add your 0.0936 and your 0.088 on the bottom, and you get 0.52. All right. So the conditional probability formula we've seen so far is a special case of Bayes' theorem, which is an application even when events have more than just 2 outcomes. So this is that sort of idea of the tree diagram. The first probability is your prior belief. And so like the woman comes in who hasn't had a test yet, our prior belief is that she is, has like a 1.7% chance of having cancer. She tests positive, and now we update our prior belief. Now she has a 12% chance of having cancer. She tests positive again, we update our prior belief, and now we think she has a 52% chance of having cancer. Okay. So the theorem is that, so say you've got probability of outcome A given outcome B is, are all the, where A1 through AK are, A2 through AK are all the other possibilities of A. Okay, so this is, this theorem is just a simple mathematical theorem. It's like the way you use it in life that affects like how you can see the world and how you can interpret things, kind of similar to that comic that I showed from the last section. Okay, let's look at an activity next. So a common epidemiological model for the spread of disease is the SIR model, where the population is partitioned in 3 groups. And so the SIR stands for susceptible, infected, and recovered. This is a reasonable model for diseases like chickenpox, where a single infection usually provides immunity to subsequent infections. But sometimes these diseases can be difficult to detect. If you're more curious about this, you should take differential equations here at Grace. We generally go into that a little more. All right, so imagine a population in the midst of an epidemic. Hard to imagine, right? Where 60% of the population is considered susceptible, and 10% is infected, and 30% is recovered. The only test for the disease is accurate is 95% of the time for susceptible individuals, 99% for infected individuals, but 65% for recovered individuals. Let me move my picture so I can keep reading. Note in this case, accurate means returning a negative result for susceptible and recovered individuals and a positive result for infected individuals. So draw a probability tree to reflect the information given above. If the individual has tested positive, what is the probability they are actually infected? So let's do the probability tree. So we've got 3 groups. 60% are susceptible, 10% are infected, 30% are recovered. And then susceptible, we've got a 95% chance of getting them correctly. Infected, we've got a 99% chance of getting them correctly. Recovered, it's complicated, so we're only getting the negative result 65% of the time. We're getting like a false positive. So then, because this is a test for that if they're currently infected. Okay, so then what is the probability that, given that they're tested positive, what is the probability that they are actually infected? And so that would be the probability of infection and positive divided by probability of positive. So then if you add up the 3 positives on the bottom, on the denominator, and then probability of infected and positive on the top, then that gives you your probability of that. So if you test positive in this scenario, there's still only a 42.3% chance that you are actually infected, because there's a large group of people who are susceptible, and it could be wrong there, and especially the people who are recovered, they are really throwing off. So that number right there, the recovered people are really throwing off the number as far as how accurate it is. All right, that completes section 3.2.